Yeah, specifically, homework 7072 due, also 73 and 74 are due. All right. So, there you go. All right. So let's take a look and let's start where we left off last time. So if you remember last time, we dealt with finding variables and we dealt with determining what type of model we're in. And we said we're going to look at 4/5 different types of models. One of them was linear models. Another was the quadratic. Another was the exponential. Another was that special rational model, where we have a linear over divided by another linear. And then I also mentioned, well, we'll be given some equations, some algebraic equations that model real life phenomenon as well, which have more interactions, more variables in them. All right. This section, we start the act of modeling, actually doing modeling. All right. So like I said earlier, the oh, somebody's on. There you go. Like we said earlier, we've actually seen some linear models. When we calculated sales tax, we had a linear model. And within the confines of a particular tax bracket, calculating income tax also gave us a linear model. Let me explain what I mean by that. What? Mouse is acting funny. So if I said sales tax is 6%, this final price is equal to 1.06 times the original price. I'll call it the original price X. That's a linear model, right? When we dealt with sales tax. So that's what all I mean. When we had an income tax, we had this equation that our tax was equal to some number I'm just going to make up, plus a certain percentage times the excess over a certain number. Well, if I call the excess over a certain number just X, that's a linear model. Okay? So within the confines of one tax bracket, we had a linear model. Within the confines of knowing what the sales tax was in a particular equation, we had a linear model. That's what I mean by we've seen some previous examples here. Okay, these are not the only linear models that we've seen. We've had other linear models as well throughout the semester. But the key thing with all linear models, how we recognize it, is it's a numerical growth. We're growing at the same speed all the time. Each additional unit that we add, each additional dollar in excess we add, translates to an increase or a decrease by a certain value. Each additional dollar on the original price creates $1.06 to add on the final price. in a sales tax setting. But it's a steady numerical growth. Right? And we've seen some of these earlier, and we've identified linear models earlier. Okay. So let's go back to our sales tax example. Sales tax in Michigan is 6%. Now, the first thing you're going to be asked to do is to create an equation. All right. It says create an equation describing how much a person pays at checkout. Then it uses the letter F when the price of an item is the letter P. Now, when you're putting this in Moodle, make sure you use the correct variables. Okay. Sales tax in Michigan being 6%. Means that you pay 106% of the original price. So just like we had on the board earlier, our final price is going to be 1.06, 106% of our original price. In this case, they asked for our final price to be displayed with the letter F, and our original price to be displayed with the letter P. So that's what I mean by make sure you use the correct letters. Using F and P. Okay. And also, just so that we're all on the same page, when you're doing these things in the Moodle, make sure that if it's a capital F, in the problem, use a capital F in Moodle. Sometimes Moodle is case sensitive, so it'll recognize the difference between capital letters and lowercase letters. Sometimes it doesn't, but just to be safe, make sure that if you have uppercase letters in the problem, use uppercase letters when you write your equation. If you have lowercase letters in the problem, make sure you write lowercase letters as your variables in the equation. Does that work? And that'll be pretty straightforward based on the scenario. Like this problem, it was pretty clear that the F here was uppercase. Pretty clear here that the P was uppercase. Now, once we have this model, which, as we can see, is just an equation. Once we have this model or this equation, then we're going to use it. We have two questions here. One of them says, how much does it cost to buy an item marked at $465? The other says, how much is the original price of an item? If you paid $123.54 at checkout. All right. So how much does it cost to buy something that's $465? How much is the original price if the checkout price is $123.54? So all we have to do, since we have two variables here, two unknowns, is we have to plug in our number into the right variable and find the other. In this case, priced at $465, that's the capital P. So in order to find F, I just need to take 1.06 times 465, and I got 492.9. So the final price is $492.90. Then it says, what's the original price of an item? If we paid $123.54 at checkout, well, that $123.54, that's going to be the final price, checkout price, final price. And so I need to solve that equation for P. Now, in order to solve for P, what we're going to do is we're going to take this equation and divide both sides by 1.06. $123.54 divided by 1.06. And then when I do that, on the left-hand side, I get 116.5471698 equal to P. What do you suppose I'm going to do there? Well, since this is a monetary amount in dollars, I'm just going to round it to the nearest cent. And I'm going to say the original price is $116.55. Right? Okay. So that's it. That's the basic understanding of modeling is just that. We create an equation that mimics a certain situation. In this case, that equation was exact. If you go in and you buy something and it's marked at $465, you know exactly how much you're going to need to pay at checkout. So these were all of the variables that we needed, in other words. So this is what we call an exact fit type model. So we have our model, we have our equation, and then we can use our equation to figure out other things. I want you to look at this problem. Example 2. Create an equation for this scenario. And then once you do that, how much revenue do you get when you sell 16 shirts? How much revenue do you get when you sell 34 shirts? And then if you want $2,500 worth of revenue, how many shirts would you need to sell? I'll flip back and forth between those thoughts. All right, so let's go through this. Because the shirts are selling at $8.50 a piece, the revenue is just going to be that number times how many shirts that they sell. If you sell one shirt, you get $8.50. If you sell two shirts, you get 2 times $8.50. If you sell 3 shirts, you get 3 times $8.50. Sell 4 shirts, you get 4 times $8.50. So the revenue is going to be, I can write this as $8.50 times N, or N times $8.50, it doesn't really matter. And if you want to write 8.5 times N, that's the same thing. Again, it doesn't matter. Notice it capitalized the R, lowercase the N, so that's why I wrote it the way I did. The revenue when you sell 16 shirts, well, N is the number of shirts, so the revenue when you sell 16 is just going to be what you get when you plug in 16 into your N. That's a revenue of 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. 136. So $136 here. Revenue was in dollars, the shirt sales were in dollars. Same thing when we sell 34 shirts, we go revenue is equal to 850 multiplied times 34. That means the revenue was $289. And then how many shirts would you need to get 2,500 in revenue? Well, we write the 2,500 in the revenue spot and then solve that equation for N. In this case, just like in the last case, the last question I should say, last type, one involving sales tax, we just have to divide by the coefficient. Of 850, when you take 2,500 and divide it by 850, you end up with a weird decimal. And it kind of depends on how this question is asked as far as what you should answer. If you want to at least 2,500 in revenue, then you have to sell 295 shirts. If you want close to 2,500 in revenue, then it's okay to sell 294 shirts. I'll interpret this as you wanted 2,500 or higher. So, sell at least 295 shirts. That makes sense. You can't sell 0.12 of a shirt. You can't sell a half of a shirt. So we need to sell whole numbers of shirts. Does that work? Pretty straightforward, I think. I hope. Now let's look at another problem. So our first two problems, they were both linear, but they're also both linear in the sense where it was just number times variable equals another variable. So let's take a look at number 3. A hauling company charges a $20 pickup fee and an additional $35 for each furniture item they pick up. Create an equation describing the total cost if you want to pick up X pieces of furniture. So I'll use C for cost. It doesn't tell me which letter to use, but that's what letter I'm going to use. Okay. Now think about the cost. The cost is in two parts. One part is the pickup fee of $20. And the other part is the $35 for each furniture item. And if you have one item of furniture, it's $35 plus the $20 fee. If you have 2 items, it's going to be 35 times 2 plus the $20 fee. If you have 5 items, it's going to be 35 times 5 plus the $20 fee. So the cost structure is going to be 35 times however many items plus the $20 fee. By the way, it doesn't matter what order you have this in. If you wanted to start with the $25 fee plus 35 times the number of items to be picked up, these are exactly the same, and Moodle will say that these are exactly the same. So you can write either one of those into Moodle and be just fine. Does that make sense? So either way, it's fine. The order of 20 plus 35x or 35x plus 20, those are the same equations. Now, once we've done that, we can ask questions like, how much does it cost to pick up 5 pieces of furniture? How much does it cost to pick up 2 pieces of furniture? And then if you have $400, how many pieces could be picked up? With that amount of money. Cost for 5 pieces, doesn't matter. Again, these are going to give you the same answer. That's why you can use either of them, both of them interchangeably. I'll use the top one. 35 times 5 plus 20. Pick up my calculator, type that in. I got 195. So the cost is $195 to pick up 5 pieces of furniture. The cost to pick up 2 pieces of furniture plug in 2 in for the number of pieces of furniture variable, which problem said to use X for that. So the cost for 2 pieces of furniture is $90. The last part of this problem says how many pieces could be picked up with $400. So we would subtract 20 from both sides after we plugged in the 400 as our cost. You should get 380 equals 35x. Then divide both sides by 35. Now, gets a little bit weird because once again we have a decimal. Roughly 86 is your X. Now, if you had $400, how many items of furniture could you have picked up? Well, you'd have 10 items, right? 10 items will be under 400, 11 items will get you over 400. So if you have $400, you can pick up 10 items. And now, items picked up. So you can have 10 items picked up. Okay. Obviously, if a furniture place lets you cut off a piece of item and they charge you 0.85 or 0.86 of an item, then you can do that too, but just what we're given here, 10 items would get you under 400, and 11 items would get you over 400. They're pretty straightforward. All right. I want you to try number 4 on your own. I want you to create an equation for the profit, and we're going to let H be number of hours they spend tutoring these two guys, Larry and Al. You can use the letter P for profit, then write that. But by the way, this one's a little bit tricky because there's one income and one expenditure that we're given. All right, so let's set up this equation. The equation is going to be the profit. Well, since they charge $30 an hour, and H stands for the number of hours they work, it's going to be 30 times H as how much they're getting in. But they have to pay $600 per month in rent. So if we do a profit equation, they're going to take $30 times the number of hours. That's going to be how much they get in. So that's going to be positive. And then they're going to have to pay out $600 in rent. So my equation is going to look like that. Profit is equal to 30 times the number of hours minus 600. Does that make sense? Since they're paying in for rent. Once we set that up, we can answer these types of questions. by the way, remember, this was the profit per month, right? Let's just be clear on that. That was the profit per month. Now, the first calculation question says, if they have 40 students, 1 hour per week, and by the way, that means 40 students, and each of the 40 students spend 1 hour per week. How much profit do they make in a month? And we're going to assume 4 weeks in a month. It's a little over 4 for most months, but. So let's actually go through that first bullet point, and we'll go back to the next bullet point. So if we have 40 students for an hour a week for 4 weeks, how many hours in a month are spent tutoring? Well, the hours in a month spent tutoring, since there's 40 students, each one spends 1 hour, 4 weeks. We just multiply those all together. 40 times 1 times 4 becomes 160. And that's the H in our problem, right? The H was how many hours they spent tutoring per month. So if we're in this scenario where 40 students spend an hour a week for 4 weeks, then our profit is going to be 30 times 160 minus 600. That's something I can plug into my calculator. And I got 4,200. $4,200. Is that okay? I want you to calculate on your own what's going to be the profit if these 2 people have 20 students. Each of their students spends 5 hours a week for 4 weeks. And then also, how many hours do they need to make $500 in profit a month? Right, both of them for. All right. So 20 students for 5 hours a week for 4 weeks. We're going to take 20 times 5 times 4, and that gives me a total of 400 hours spent tutoring. When I take 30 times 400 and subtract 600, I get a profit of $11,400. Oops, $11,400 for the month. If we want to make $500 in profit, or if these two guys want to make $500 in profit, we're solving this equation. So we're going to add 600 to both sides. That'll give 1,100 is equal to 30 times H. Then divide both sides by 30. And we get an H, which is equal to 36.666667. That's just rounded, obviously. And so how many hours? I guess if they did allow to charge a partial hour, then you'd say 36.67. So if they could charge a partial hour, you'd go 36.67. If they couldn't, you'd say 37 hours. Does that make sense? Okay, again, this is if partial hours are allowed. If full hours only, then you gotta go 37. That makes sense? So if these two guys allowed to charge, you know, for 40 minutes and they that's what'll happen. Any questions about that? They're pretty straightforward. Now, one other linear equation, and this kind of will motivate the last part of this chapter as well. One other linear equation that I'll bring your attention to is one that converts Fahrenheit to Celsius or Celsius to Fahrenheit. It turns out, if I ask you, what's the equation where you can convert Celsius to Fahrenheit? Most of us probably wouldn't know it off the top of our heads. Okay. But it's something you could look up. You could search it on the internet, and you'd find out that the equation that converts Celsius to Fahrenheit is 9/5 C, which stands for the degrees in Celsius, plus 32 is equal to F, which stands for the degrees in Fahrenheit. Okay. So it's not something that we created, it's something that just simply exists. I didn't create this. But you can still answer questions. You can say, what's the temperature in Fahrenheit if we're at 30 degrees Celsius? What's the temperature in Fahrenheit if we're at negative 40 degrees Celsius? What's the temperature in Celsius if we're at 0 degrees Fahrenheit? Or what's the temperature in Celsius if we're at 98.6 degrees Fahrenheit? So these are a little bit easier. Going from Celsius to Fahrenheit, a little bit easier because I can just take my equation and plug in whatever number I want. In this case, we start by plugging in 30. And then it's really easy to plug in 30 on our calculator. I just take 9/5 times 30 plus 32. And the Fahrenheit temperature is 86 degrees. Again, Fahrenheit. If we're at 30 degrees Celsius. That makes sense? At negative 40 degrees Celsius, we should all know temperatures can go into the negatives, right? I just take 9/5 times negative 40 and then add 32. And interestingly enough, you get out of negative 40 in your degrees Fahrenheit. So negative 40 degrees Celsius is the same thing as negative 40 degrees Fahrenheit. That's a little weird trivia fact. What temperature do Celsius and Fahrenheit have the exact same measurement? It's at negative 40. Okay. Negative 40 degrees Fahrenheit is negative 40 degrees Celsius. It's one of those little tidbits of trivia. And that's the only place that they match up. That's the only place that they match up. Every other temperature, the numerical degree is different for Celsius and Fahrenheit, except for negative 40. Negative 40 is the only spot. And then we can do the reverse too. We can plug in 0 for our F and then solve for C. We'd subtract 32 from both sides and then divide by 9/5. When you divide by 9/5, make sure when you're dividing by 9/5 that you put that in parentheses. Otherwise, it'll do divide by 9, and then it'll take your answer and divide by 5. You don't want to do it that way. So you want to make sure you have parentheses around the 9/5 when you divide that. And what you end up with is negative 17.78 degrees Celsius. Lastly, the last linear problem in this section we're going to do is figuring out what 98.6 degrees Fahrenheit is in Celsius. So we got 66.6 is equal to 9/5 times C. Once again, when you divide by 9/5, make sure you do so in parentheses. So the degrees in Celsius is 37 degrees Celsius. So if you're talking about body temperature to somebody who doesn't typically use the Fahrenheit system, you say the standard body temperature is 37 degrees Celsius. Right? Most of us know that standard body temperature is 98.6 degrees Fahrenheit, but now we know it's 37 degrees Celsius. Same thing. That's for humans, obviously. Do you know other animals, other mammals have different standard body temperatures than we do? Like horses and cows and they all 98.6 is just the number for humans, but bigger animals, smaller animals have different Fahrenheit temperature of their sitting, resting. Okay. I don't know what many of them are, I know they're different. So that's linear models. As you can see, we either create a linear model or like in the last problem, we're given a linear model. And then we end up using it. Now we're going to move on to the exponential models. All right. The previous examples involving exponents were our lump sum interest calculation. A equals P times 1 plus R over N to the MT. And we also had an exponent when we dealt with annuities. Now, in this part of the section, I'm not going to deal a whole lot with that annuities, but this interest equation will come up in different venues. Okay. This is interest compounding M times per year, or growth happening M times per year, or decay happening M times per year. And it doesn't have to be monetary, it doesn't have to be money, it can be any sort of growth that happens 5 times a year, 4 times a year, 12 times a year. Okay. So whenever we have percentage increase, where we have a certain number of times per year, we're going to have that A equals P 1 plus R over N to the MT. Example. Okay. Now there's one other example that we're going to deal with as well. And the other example is going to be when we compound continually. That means we're always in a state of growth. If we are compounding continually, then I'm going to use another special type of exponential function. And that function is A equals P e to the RT. So these are the two primary equations that we're going to use. Right? There are other exponential equations that we could use, but these are the two primary ones that we're going to rely on. Either in compounding m times per year, which is the same equation that we had earlier with the lump sum and the banking stuff, or compounding continually. Now, E here is not a variable. E is a special number that comes up when you look at natural growth, all right? E actually is an irrational number. It's about 2.71828, blah, blah, blah. Okay? And actually, it's on our calculator. So it exists on the calculator. And remember, you could have gotten either calculator. There it is. E to the first power is 2.71828. This is on the TI-84. When you're trying to find E on the TI-84, it's actually the second button, and then this button here that's right next to the 4. It says LN, and then it has an E to the X. The vast majority of times E is used is with exponential functions. So because of its connection to exponential functions, they put it in there as E to the X. If you don't want it to have an exponent, then you do a second divide sign. But almost always we want to have E have an exponent. So it's second and then that key there. Now on the other calculator, E also exists as an exponential function right there. So if you have the TI-30, you just hit second and then again the LN. this down a little bit. And then you can e to whatever power you want. Again, if I put e to the first power, 2.71828, et cetera, et cetera. Does that make sense? So on the TI-30, it's second, and then that button right there, e to the x. On the TI-84, it's second, and then the button is right down next to the 4. This one, ln. Second ln, both calculators. Any questions about that? Where the E is? E is just a number on your calculator, all right? It's like pi. Pi is a number on your calculator that you can just type in. Same thing with E. And E is also irrational, just like pi. It just keeps going without repeats. But it's very, very useful in natural growth type scenarios because of its connection to the compounding continually growth equation here. All right. So let's do a couple of examples. All right. Example 1 says, we invest $4,000 into an account growing at 7% interest compounded monthly. Write an equation describing how much you will have, we'll call that A, after T years. So if we're gonna put in $4,000, growing at 7% compounded monthly. The first thing I need to do is decide which one of these versions am I going to use. Since we're compounding monthly, that's an M times per year version. So compounding monthly means that M is going to be equal to 12. All right, so N is equal to 12, and I know I'm going to be using this equation. And I just put the numbers in the correct spots. P becomes 4,000. 1 plus my rate is 0.07. M is obviously 12. So there you go. That's the equation that I need to use. This is the model, the algebraic model for determining how much you have in the account at any given point in time. Just like before, once we have that model, we can say things like, how much will you have after 10 years? How much will you have after 30 years? How much after 10 years? How much after 30 years? Okay, so if we say how much after 10 years, all I'm doing is putting 10 into the value of t. When I type that into my calculator, often I'll say 12 times 10 is 120. We dealt with that earlier in the semester. So I'm just going to put in 1 plus 0.07 divided by 12 to the 120th power. And because we're talking about money, we'll round this to 2 decimal places like we normally would. $8,038.65. And if we do the same thing for 30 years, we simply plug in 30 into the t. $30 times 12 is 360. So if you want to use the 360 as your exponent, just to make things a little bit clearer, you can do that. And you would end up, after 30 years, having 32,465.99. All right, rounding to 4 decimal places, obviously. Again, what a difference an extra 20 years makes. What a difference. Any questions about this? No. Let's do one more before we leave. This says unchecked rabbit population grows at 68% continual. 68% continual growth. How many rabbits would exist in unchecked conditions after T years if we start with 10 rabbits? So we're starting with 10 rabbits. And we want to create an equation for how many rabbits exist after 10 years. Or after T years, excuse me, T years. Okay. Now, because it says continual growth, I'm going to be using this equation here. Growing at m times per year, I use this equation. Growing continually, I use this equation. So I'm going to use this equation because we have continual growth. And you can imagine what these letters are standing for. A stands for the amount you have. P is your, quote, principal. In this case, it's just the starting amount of rabbits, right? Just like if we put in $10, now we're putting in 10 rabbits. It's the initial amount. R is still your rate of growth. So in my case, it's 0.68. And then the T is the number of years. So there's your equation. By the way, just so that we're all on the same page, in Moodle, what you're going to have to write is A equals 10 E, and then you'll have to put a caret, and then 0.68 T. Does that make sense? You have to use that caret symbol to get into the exponent, and then when you put the exponent in, you'll want to put that exponent in parentheses so that 0.68 and the T both end up in your exponent. Does that make sense? So caret, and then in parentheses, the 0.68 T. All right. And then we can answer questions like, how many rabbits are there after 3 years? And then how many rabbits are going to be there after 8 years? All right. So how many after 3 years? How many after 8? And it's pretty straightforward. A equals 10. E to the 0.68 times 3. When you type that in on your calculator, I'll type it on my TA84. You simply have to put 10 and then go to your E button, and then in parentheses put in 0.68 times 3. All right. But make sure you're using that E button. And the same thing is true on the TI-30. It's going to be 10. Use that E to the power button, 0.68 times 3. Make sure the 0.68 times 3 is inside of parentheses, especially if you're using the TI-30. Okay. But in both cases, you get about 76.91. So probably you're going to have either 76 or 77 rabbits there. You can't have 0.91 of a rabbit. So probably 77 rabbits. This isn't going to be an exact thing because we're talking about rabbit populations. So about 77 rabbits. And then if we want to do it with 8 over 8 years, we just change that 3 to an 8. And all of a sudden, we have 2,304.42 rabbits. So 2,304, 2,305, who knows how many will, die and get hit or get hurt, but approximately that many. That work? So that kind of gives you an idea of how to use this equation. We've already used this equation a number of times. So if you want, you can try that 7-3-7-4 homework. You have all the tools you need to do it. I think that 7-3-7-4, 7-3 and 7-4 homework, I'm gonna delay till next Friday. All right, because we're not quite done with the exponential stuff yet. We just have a couple more examples to work out. But it's all very, very similar to this. We're either using this one or we're using this one. Okay, compounding continually. Use the E, compounding n times per year. Use the interest formula that we already knew. Does that work? All right, so I'll delay that one homework, but the 7-0 through 7-2 homework, that is still due this Friday. So make sure you get the 7-0, 7-1, 7-2 homework done by Friday at 5. All right. All right, well, that's all I have for you, and I will see you next Tuesday.